Okay, good. So, yeah, I hope, let's say, welcome back again. And I hope the midterm exam was, let's say, doable. And let's see if by the end of this week, I hope I can finish the grading. So let's see. And now we learn about the kNN, k nearest neighbors, and we can use kNN for classification as well as calculation. So what is classification? Well, it's a kind of supervised learning, and we want to predict, let's say, the output label based on the input data. And then the output label for classification is categorical, and that's what makes it different to regression, because for regression, the output label is numerical. But both the classification and the regression, they are all supervised learning, because the learning process is that they learn from the pairs between input features and output labels. Okay, okay, let's see. So kNN classification. We first, let's set some assumption. So the assumption is that similar inputs would have similar outputs. Right? And then now we are talking about using kNN for classification. So let's see. Um, yeah, okay. So classification is that given some test input, you predict the class of the input, right? For kNN, the idea is that given some test input x, right? This is x. The task is to classify x. So in this case, we assign the most common label of the k nearest neighbors of x. In other words, it's k most similar training inputs to x, right? So I think it's easier to explain with an example. So we have this example. Let's say this is our data set, and then we have the training data. So this is classified as red and cube shape, and then this is classified as blue in, let's say, ball shape, right? And then the task is binary classification, right? We shall also set the k, the number of nearest neighbors we are considering. Let's suppose that k is 3. So 3 nearest neighbors, okay? And now let's do some prediction. Let's suppose that our data, our new data is x, right? And then we might wonder, so how to classify x, right? Well, the name is k nearest neighbors, and then at the moment k is set to 3. This means that we need to look for 3 nearest neighbors of x. If you look at this data set, right, which are the 3 nearest neighbors? We need to compute the distance of x to all the data points. So for example, the distance between x and this, and then the distance between x and this, the distance between x and this, and the distance between x, this, and this, and so on, right? And having computed the distance, we can now figure out which existing data points have the shortest distance to x. So we rank the existing data points based on the shortest distance, right? If you look at this example, I think it's quite easy to see that the three nearest data points to x would be this, this, and this. Why take only 3? Because now we are dealing with k equals 3. It's 3 nearest neighbors. Okay. And what's next? So having found the 3 nearest neighbors, then we observe most common label among the nearest neighbors. So let's see, with respect to the 3 nearest neighbors, we have 1, 2, 2 blue labels, and then just one red label, right? And then we already know which label is the most common. In this case, it's the blue one, okay? Because 2 blues versus 1 red. Okay. So that's the basic idea of kNN classification. And if you have any question, just let me know. Okay. And you might wonder, so previously I said k to 3, but what if we set k to, let's say, different number? Consider this example. So it's a different one to the previous one. So we have two different classes, the yellow class and then the purple class, right? And then this is our new data point, right? We don't know yet if it would be better to be assigned with class A or class B, right? Then we look at the effect of different case. First, let's suppose that k is 3, okay? K is 3, and then we see the 3 nearest neighbors to this star. Okay, I think it should be clear that the 3 nearest neighbors would be this, this, and this. And if you can see, the most common label would be the purple one. So when k is 3, the new data point will be labeled as purple, right? Okay, let's see. If we have, let's say, k equals 6. K equals 6. Let's see if we might have even different classification result. Okay, let's see. So now, suppose that k equals 6. We want to get 6 nearest neighbors, right? You see, now there are like 1, 2, 3, and 4 yellow classes near the star. And then there are just 2 purples, right? It's 4 against 2. This means that the majority label is yellow instead of purple. So what does this mean? This means that different case might affect the classification results. as shown by this example, right? It doesn't mean that it has to have different effects, no, but it might have different effects. Not always, but it might have different effects. Okay? Okay. Is there any question so far? Not yet? Okay. Now let's do it step by step. We are doing kNN classification. Okay? We have x and y axis correspond to two different features, right, of the data points. And then we have two classes, class A, red star, and then class B, green triangle. And we have this new data, new example to classify, right? So you must first calculate distances to all other data points. So from this new example here, 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 and so on. So you have to calculate distance to all other data points. And then you find neighbors by ranking the distance, right? So from the shortest to the furthest, right? So when k equals 3, the three nearest neighbors would be this. And you do the majority voting, get the label, right? So there are two greens and then one red. This means that, okay, then this new example, new data point will be classified as green. Okay, okay. So now a question for you. So I'll give you 5 minutes to think about it and to devise possible answer. So take a look at this figure and what distinguishes the kNN classification when k is set to 3 versus k is set to 5. So 5 minutes from now. So you can answer the question via the Zoom chat, feel free, or you can just, let's say, unmute and then say the answer. I got one answer, but I'm not sure if it's the correct one because it's actually k equals 3 versus k equals 5, not 6. Okay, I got a couple answers. Let's see. If k is 3 in data is included to the red class. Yes, that's correct. If k is 5 in data point is belongs to the blue class. Okay. And also another answer, when k is 3 it's red. When k is 5 it's blue. Now my question to all, what about when k equals n? N is the number of all. Mhm. So I have a follow-up question. So if you have some uh, answers, just let us know. Might be a bit tricky. Include the green one. I'm not. Maybe not because green one it's doesn't have any plus yet now. It doesn't include the green one yet. It's a tricky question. Okay. What happens when k equals n? Yeah, I got one answer. Looks good, but let's wait for some other participants, other students. If you have any opinion, any comment, any answer, let me know. Or if it's still unclear, just let me know as well. Okay, so the answer from now there are two students with the answers. Great. So let me tell you the first answer by the student. In my opinion, if k is the number of all data points, it can either be red or blue. Well, since the numbers are the same for each. Okay. Yeah, we have four reds and then four blues. So you can, let's say, toss a coin, do the random selection. And then second answer, if we go with what we have already learned, it will be a tie. Okay. We might try using k equals n minus 1. I think this is also a good answer because one way to escape the situation would be, well, to have an odd number of k, and then the nearest odd number would be n minus 1 when k is even. Okay, nice. And also another remark from a student, I believe that if k is n, you pick the largest class. Exactly. Okay. And also another insight, we can use the distance to determine which is closer to the data points. That's also true. We can do, let's say, weighting. So weighted voting. Because let's say if some data points are closer to the new data point, then they should be weighted more than further data points. Yeah, great. I think yeah, all the answers are complementing each other. This is great. Thank you. I think then we can move on. Yeah, and then various distance measurements, we can use the Euclidean distance, right? I think you should be quite familiar with this distance metrics, because I think you have learned the distance metrics during our clustering class, right? And also the Manhattan and the Minkowski. Okay, so when if you look at the Minkowski, when Q equals 1, then the Minkowski would become Manhattan. And then when Q equals 2, then the Minkowski would become Euclidean. Right? So just to refresh you, so what's the Euclidean distance between P1 and P2? Because it's two-dimensional, we can rely on this good old Pythagorean theorem, right? Here's the computation, right? It's the difference, square difference, and then you compute the square root, and then that's it. We get 5, this one. This would be the Euclidean distance between P1 and P2, okay? I mean, you can also plug in the Pythagorean theorem, and then you'll also 5, okay? Good. And then let's see, what about this Manhattan distance? So Manhattan distance, I'm writing it using Notepad, so you know it's not that easy. Manhattan distance between P1 and P2. Does anyone know? You should know. We have this formula, right? So what's the Manhattan distance between point P1 and point P2? Let us know. I mean, you just need to add this and that. Let's see. So here's the formula. It's basically the absolute difference, the sum of the absolute difference between, let's say, each value. So let's take a look at this sample. Distance between 5 and 1, it's the absolute distance is 4. Between 4 and 1, it's 3. Then you just have to compute the sum. So it's actually 7, right? It's basically 4 plus 3, then it's 7. Okay, that's the Manhattan distance. So you should be able to compute both the Euclidean and then the Manhattan distance, right? And the Minkowski distance, well, you might use it for any advanced applications. Okay, then let's see how we can use this kNN algorithm for some data set. We do some coding. So we have now this iris data set, right? And then, well, you should know this iris data set, right? It's the Hello World data set of the AI and data science people. Right? So here's the iris flower. quite beautiful. And then for features, so the length and width for this, and then the length and width for this. The sepal length, sepal width, and then petal length and petal. There are three different species of the flowers: setosa, versicolor, and virginica. Right, and we want to do automatic prediction of the iris species based on the four features. And since we are now on this class of kNN, we are now using kNN. Okay. I think there is like the mailman delivering a package. So sorry, so just a second. Okay, sorry. Yeah, I'm back now. So I have the Google Colab file for this small exercise. So let's see. It's available here, but I want to share it to you so that you can try it out as well. Okay. Yeah. So let's see, what do we have here? This is kNN iris classification and then some library import. This is to load the iris dataset, the feature names, the data, I mean the feature values, the target names or the class labels, and then the labels for each row, right? So let's just run it. Okay. What are the feature names? We have sepal length, width, petal length, width, and then some uh, values. And what about the target names? We should have Setosa, C color, and Virginica, and also class labels for each row. Right? And to have like a better view, so we can use this pandas data frame, right? And then here you have, let's say, cleaner look at the data set. So the zeroth row, the sepal length, the value is 5.1 centimeter. and then the sepal width is 3.5 centimeters, petal length 1.4 centimeters, petal width 0.5 centimeters, and then it is categorized as class 0, and class 0 is Setosa. Okay? Right, and so on and so forth. So you can look at all the data set here, something like this, right? And yeah, something like this. Okay, next, we do the splitting, right? We need to do the splitting because we want to have the train set and the test set, right? But let me give you a hint on the idea of the train and then test set. Okay, so here's our this is our data set, the full size of our data set. And then if we want to, we are doing machine learning, so we are learning from the data, right? Okay, we are learning from this data, right? But then if you learn from this data and you also test on what you have learned over the same data, then I think you'll get like seemingly best mark, best grade, right? But since you are testing yourself on the exact question answers based on what you have learned, so it might be that it's not really representative on your learning, what you have learned, and then the generalization of what you have learned. And that's why the idea is to split the data set into two. So the train set, this is the train set, and the test set, right? So now we have the test set, right? Then this is clear. So over which part of the data set we do the learning, training, they are more or less the same. And then over which part of the data set we do the testing, right? So from this, you will have your model, prediction model, right? This is the model. And then you want to evaluate, you want to test your model, your prediction model over the test set. You test it. This way you will get, let's say, a fairer result, more representative evaluation result compared to testing over the same train set, right? So that's the idea of the splitting between train and test sets, right? Okay, let's go back here. And then this is the code to do the splitting. Test size equals 0.2. This means that the size of the test set is 20% of all the data set. Okay. Okay, let's run it. Great. So let's see. Now we are constructing a kNN classifier, and then the number of k, in this case, I don't know why it's called n, but let's stick with this. The number of neighbors, nearest neighbors to be considered right now, it's just one. What does this mean? So let's take a look. So this example, you see it's 3NN versus 5NN. If it were just 1NN, so the decision of this of the class of this would be determined by the just the closest, just one closest data point. It's actually this one, right? So it will be classified, this will be classified as friend. Okay, that's for one nearest neighbor. Okay, let's see. And then you do the fitting and then you do the prediction, right? So the prediction is what we have done here, right? You basically have to calculate distance to all of the data points, get the nearest neighbors depending on the number of k, and then do the majority voting. That's this one, predict. And then we output the accuracy, right? So out of all predictions, how many are correct? Okay. So let's see, let's run this one. Okay, 0.9. Out of 10 predictions, 9 are correct. I think it's quite good, but recall that we are dealing with this iris dataset. So it's like one of the uh, first datasets, initial datasets. So it might not be that complex, might not be that complicated, uh, yeah, compared to other datasets, right? Yeah, with the k equals 1, so you have this as the accuracy. Let's try to add the number of k's. Now it's 2. Let's see if the accuracy will increase. No. What about 3? Wow, quite good, right? Some improvement. But I think to test it like one by one, it might be a bit exhausting. So let's just do this in like loop. For k in range 1, comma 11, this means it will try. So k will be set from 1, 2, 3, so on up to 10. Okay. And then we'll see which k is the best. Okay. Let's run it. So when k is 1, the accuracy is 0.9, 2, 0.9, 3, 0.93, 4, 0.93 still, 5, 0.93. Now we have some improvement. 6, the accuracy is 0.96, 7, 0.96, and we get even the perfect accuracy if we set k to 8. And then the performance drops, right? This is amazing, right? That we we, we can get the perfect accuracy. But again, we should take into account that we are dealing with, let's say, a Hello World data set, like the ARIS data set. It's one of the first data sets for AI and data science learning. Okay, okay, that's for the kNN ARIS classification. Is there any question from your side? Not yet. Okay. Maybe we can see. I have another data set. This is actually the kNN diabetes, right? So it's more advanced than this kNN iris data set. So now we are dealing with diabetes. Let's see. So let's run this Google Colab. First, we import the Python libraries as needed, and we load the dataset, visual dataset, and then print the first 5 rows of the dataset or the data frame. If you look at this, you know that there are several features, pregnancies, glucose, blood pressure, skin thickness, and so on. And then the outcome would be the output label we want to predict. In this case, because we are dealing with diabetes, so it's whether it can be predicted as diabetes or not. Okay, so let's see how big is our data set, which is 768 rows and with 9 columns 1, 2, 3, 4, 5, 1, 2, 3, 4, with 9 columns, including the output label or the target. Okay, so now you have the yeah, I mean, if you look at this outputs the Y or the outcome, the diabetes evaluation result 1010 and so on. So there should be like 768 data points here. And again, we do the train and testing splitting as before, right? And then we would like to have a test size of 40%. That's quite a number. It's, let's say, usually it's set as 0.3 or even 0.2, but now we have 0.4. Okay. And so we'll use the k nearest neighbors classifier. So for this diabetes data set, right? And let's see. Okay. So we'll perform kNN classification, right? But first, we want to set up the number of neighbors. And then we want also to measure the train accuracy over the train set and then accuracy over the test set, right? But let me run it. Great. And yeah, for each iteration, you do the kNN classification with different number of case. You fit the model and then record the accuracy over the train set and then accuracy over the test set, right? And then you draw the plot with respect to different case over the diabetes data set, and here's the result, right? What can we observe from the result? I think let me give you some time, maybe 3 minutes to absorb, to grasp the results, and then we can share what we can find from these line charts. Okay, so yeah, we are doing kNN with the different number of k's, nearest neighbors, and with the different, let's say, over different sets. So test set versus train set. And then we can observe some interesting things. For example, the training accuracy is always higher, even like the differences. So start, the gap is very large here, see? And it's always above the test accuracy, right? Why? Well, it's quite, let's say, I hope it's quite obvious because as I said before, for getting the training accuracy, so you do tests over the data set that you also did the training. So it's like you read a book and then with some question answers, and then you take tests with the exact questions from the book. Then of course it will be easier than you get exams with different questions. Of course, the training accuracy should be higher than the testing accuracy, right? Okay, so I mean the difference is like over 30% for the k equals 1, right? And then but the difference is getting like closer, right? When the number of neighbors uh, increases. Okay, and then what's next? So I think in general, so having let's say low number of neighbors like 1, it's actually not so good for training accuracy, but we have to be careful. Do we really want to have like best training accuracy or not? In general, the answer is no, because in general, you will be test over even new data. So the data that is so new that you never see it before, right? And that's why you want to have like high testing accuracy. Well, if possible, like high training and high testing, but if you have to pick one, then pick the highest testing accuracy, right? And then the answer is this one. So I think the best K for the highest testing accuracy is actually when the number of neighbors on K equals 7. Okay, that's it. So in this example, we've just done so-called hyperparameter tuning, right? So you pick the hyperparameter. So in this case, it's k, the number of neighbors, and you pick one, giving the highest testing accuracy, and that is 7, right? Why 7? Because if you pick, let's say 8, then the accuracy could become even lower. So too low k is not good, too high is not good either. So the best k in this case is 7. Okay, right. And then we set up kNN classifier with k neighbors, and we fit the model, and we get the accuracy, and it's actually 0.73. This is 0.73. Okay, that's it for the diabetes data set, right? It's more it's like having more columns than the iris data set, and I think it's like it's still far from a real data set, but at least it's a bit more advanced than the iris dataset. Okay. Good. I'm not sure if I have shared this to you, just to be sure, so I'm saying it to you. All right, so let's go back to the slides. I think a possible exam question. We'll do another exam, the final exam. I think in I forgot, like May or June. I think it's like May or June. And then well, you should know the difference between different case, and then you should know how nearest neighbors classification work, and then how different distance functions might give sometimes different results. Okay, so yeah, let's see. So k in for iris data set, k equals 0, it's actually more accurate than k equals 1. So let's see. I think we have it here for experiments. Okay, k equals 10 is more accurate than k equals 1. 0 0.96, 0 0.9. Okay, still valid. But can you see why? So let's take a look at this example. Okay, we can see this like as a classification results, prediction results, right? And the prediction results are different. There are two models. So the black one and then the green one. Okay. And then if you look at the first, look at the green model. The green model, even though if you look carefully, it seems to have like perfect, even like perfect accuracy for the training data, right? Awesome. But this is overfitting. It's not really generalizable. What is overfitting? So it's like when you want to fit too much, right, over the peculiarity of the data, even noise. It's like when you wear like a t-shirt that is too tight for you, right? It's not good. I mean, maybe it's so fitting to your body, you don't feel good anymore when you wear like a very tight t-shirt, right? And again, I mean, does it mean that we have to wear like very loose t-shirt? No, of course not, right? A very loose t-shirt would be something like this, something like this. This is just so wrong, right? This decision boundary for classification. This is not good. So the best one in this example is actually this one, the black model, right? So it's generalizable, and it's not fitting too much over the noises, but it still follows the general, the major pattern of the data set, and that's why it's good, right? It's like when you wear clothes that are just perfect, not too loose, not too tight. That's the generalizable model. Okay, we saw this one, kNN classification for diabetes, right? So some advantages and disadvantages of the kNN. I think it's quite intuitive, and then it's very easy to update the model. Well, you just add new items, and then the computation will check the distance to the new items if the new items would be one of the nearest neighbors to your data points. And then some disadvantages. It might be expensive. You have to compute distance to all, and then you have to store all the training examples. And then you have to be careful in how to set K, right? The hyperparameter tuning. So we should do the hyperparameter tuning first, right? Which means some preprocessing we have to do. Okay, so another question is how we can do kNN for regression, right? So see, so here's the data point. This is like when x is 1, the output is 4. When x is here, the output is 6. When x is this, the output is 6. When x is around 5, the output is 3. When x is 6, the output is around 2. So there are our data points. And then for regression, the output is numerical. So this is numerical, right? And then let's say if you do so-called polynomial regression, so the best fitting line would be like this. This would be the best fitting line. Okay, but can we do kNN, right? Question is, can we do kNN for regression? The answer is yes, but let me clean up the stuff here. Okay, so the question is, if your input feature is 4, like what would be the output label? What would be the predicted output, right? Okay. That's the question. So can you guess what would be an answer? So then it again depends on whether you do 1 nearest neighbor, 2 nearest neighbors, 3 nearest neighbors, and so on, right? So first, let's focus on 1 nearest neighbor. What does this mean by 1 nearest neighbor? You pick just one, the nearest neighbor, to determine the output, the regression output. Okay. So as shown here, when you pick 1 nearest neighbor, and when your input is 4, the output will be predicted to be here. But why? Why here? So imagine 4 is like this one. When x is 4, it's actually this one. And then you try to look at the other data points. So this and this and this. So the point now is, well, pun not intended, but the point now is that we want to check again still the nearest neighbors. The nearest neighbor to 4. What is it? So you just compute the distance between this and this, between this and this, between this and this, this and this, this and this. And obviously the nearest neighbor is this one, right? 1 nearest neighbor, and then that's it, done. You just predict the output based on 1NN, the nearest neighbor. So it's actually this one. So you'll have the same value as the one when the x value is 3, and then your prediction will be 6. That's if you do the 1 nearest neighbor. What about 2 nearest neighbors? Question is, which are the 2 nearest neighbors? For the data point when x equals 4, right? That would be this. Of course, this should be included, and this one. Okay? So the value of this is 6, the value of this is 3. The middle is, the average is around 4.5. So if you do the two nearest neighbors, right? So when the input is 4, the output will be 4.5. And what about three nearest neighbor, right? So when you do three nearest neighbors, so it's like you get this, and then this, and then this, and then the average should be this one. So that's why when your input is 4, then the output will be predicted as this one, 3.7 something. Okay? But in my opinion, in this specific example, it's best to have to NN because it's the closest to this, to the real curve generating the data. But of course, you don't know, right? Uh, in the beginning, of course you don't know this regression curve, right? That's it. Yeah, and then you can also do kNN regression for this, for given the passage time, you predict the journey length. So for different uh time points, right? This, this, and this. So how would you do that? Suppose we'll do one nearest neighbor, three nearest neighbor, and five nearest neighbors. I'll give you around 3 4 minutes to understand why is this like this, why is this like that, and why is this like this. Right, 3 minutes. Okay, so let's do the one nearest neighbor to predict the journey length for the three new uh time points. So let's say this one. Obviously, the nearest neighbor is this. So then your predicted journey length would be exactly the same as this one. And also same idea. Predicted would be this one. Same idea would be this one. I think it's quite easy for the one nearest neighbor, but it's also not that hard for the three nearest neighbors. The main point is to compute the average, right? So, for example, this one, the three nearest neighbors would be this, this, and this, right? This is like quite close, but not really, because we have to take three nearest neighbors, and then the average will be this. And also for this one, the three nearest neighbors would be, let's just take an example of this one. I mean, it should be this, this, this one. I think this is correct. So the average would be this. So the predicted journey length for the departure time of this time would be this one. And also for this one, right? The nearest neighbors would be this, this, and this. So the predicted journey length would be this one. And also for five nearest neighbors, but I think with respect to this example, five nearest neighbors do not look that good. So but let's see, five nearest neighbors to this would be this, 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 and this, quite a lot. And then the average would be this one. And then for this one, the average would be this one. And for this one, the average would be this one, right? Okay. Yeah, okay. So that's the idea for the kNN regression, right? And we have also, first we have seen the kNN classification, and second, we have done the kNN regression. The the core point, the essential point is more or less the same. So first you need to find, to do hyperparameter tuning to get the right K, right? The right number for the nearest neighbors. And then you pick the distance measurement, distance metrics, Euclidean or Manhattan, or even cosine similarity if we are dealing with the text data. And then you compute the distance to all the data points, excluding yourself, of course. And then you rank the distance from the shortest to the largest. And then we pick the top, say top 3, top 5, depending on the K, right? And then you pick the most common label. You do the majority voting. That's for the classification. While for regression, you compute the average, right, of the k-nearest neighbors, right? So, and that's it for I guess for today's class. Is there any question?